We will discuss here properties of logarithmic function y equal logarithm to the base a of x. We will use the fact that logarithm is the inverse of the exponential function y equal a to the power x. We will use the general properties of a function and its inverse to establish properties of logarithmic functions. We'll focus on the case where a is greater than 1. For a between 0 and 1, the discussion and hence the properties will be generally the same. Properties of exponential function are listed on the left. We'll use them to generate properties for the logarithmic functions. We'll start with the domain and range. Since the domain of a function is the range of its inverse, we can say that the range of the logarithmic function is interval from -infinity to +infinity, which means that a value of a logarithm can be any real number. Also, the range of the function becomes the domain of its inverse, so this tells us that the domain of a logarithmic function is interval from 0 to +infinity. That means that the logarithm to the base a of x exists only when x is greater than 0. It is very important to remember that restriction on the domain. Logarithm to the base a of x does not exist when x is negative or x is 0. The graphs of a function and its inverse are symmetric about the line y equal x. So knowing the graph of an exponential function, we can obtain the graph of corresponding logarithmic functions. Since the points -1, 1 over a, point 0, 1, and 1a are on the graph of the exponential function, then the following points are going to be on the graph of logarithmic function. It's going to be 1 over a, -1, 1 and 0, and a and 1. There is also one more thing to discuss here. The exponential function has a horizontal asymptote. It is x-axis. Now, when that horizontal line is reflected about the line y equal x, we obtain a vertical line x equals 0. So, a logarithmic function will have a vertical asymptote with the equation x equals 0, which is simply y-axis. So once we have the points and we know that the y-axis is the vertical asymptote, we can draw the graph. So let me plot the point. Point is 1 and 0, 1 over a and -1 will be somewhere here, and the point a and 1, according to our formula, is going to be somewhere here. The symmetric graph will have the following shape. This is the logarithm to the base a of x. Notice asymptotic behavior. Notice the symmetry. You can see that the function has the x-intercept, that x-intercept is the point 1 and 0. There is no y-intercept. Okay, the other properties of the logarithmic function are similar to the properties of exponential functions. This is a one-to-one function. It passes the horizontal line test, and therefore it has the inverse, and the inverse of logarithmic function is an exponential function. Also, because it's one-to-one, we can write a similar statement as for exponential functions. For exponential functions, we could say that if two exponents with the same base are equal, then their powers are equal. We can write the same statement for logarithms. If logarithm to the base a of u is equal logarithm to the base a of v, so if two logarithms with the same base are equal, then we can say the inputs are equal, so u is equal v. And we'll use this property to solve some logarithmic equations. The last two properties listed here are general properties for the inverse and the function, and if we apply these properties to exponential function and logarithmic function, we will obtain the following. F, which is the exponential function, to the power logarithm to the base a of x, that's going to be the same as x. This is identity if you compose those two functions. This is for x in the domain of f inverse, so this is true for x is greater than 0. And the last property can be rewritten as a logarithm. That's the inverse logarithm to the base a of the f of x, which is a to the power x. And this is also going to be x. This is for x and a real number. As mentioned earlier, the properties of logarithms with the base between 0 and 1 are the same as for logarithms with the base greater than 1, with one exception, the graph, since the graph of exponential function with a between 0 and 1 is different than the graph for a greater than 1. The generic points on the graph of logarithmic functions are going to be still 1 over a negative 1, 1, 0, and a 1, but because a is now between 0 and 1, 1 over a is greater than 1, so 1 over a and negative 1 is going to be somewhere here compared to the graph of our exponential function. Then we'll have point 1 and 0, and a and 1 is going to be somewhere here. As before, the y-axis is the asymptote for that graph, so symmetric graph to that exponential function will have this shape. And this is the logarithm to the base a of x with a between 0 and 1. We'll mention here two other logarithms with the special names. One is the common logarithm, which is denoted just log x. This is simply logarithm with the base 10. So if you see just log x, that means that the base of that logarithm is 10. Below that, we have a graph of that function. The base a is 10, so we'll get point 1 over 10 negative 1, 1 and 0, and the point 10 and 1. The base is greater than 1, so the graph resembles that graph for a greater than 1. And the other logarithm, very important, is natural logarithm. It has its special notation. It's denoted ln of x. This is logarithm with the base e. This is the inverse of natural exponential function. And as before, since the base is greater than 1, the graph will have the shape of that for a greater than 1, and the points are 1 over e negative 1, 1 and 0, and e and 1. Remember that e is that irrational number close to 2.7.